Euler Finance was a lending protocol in Ethereum that had an incident around March of 2023, and this amount of money was stolen from users, from investors, and other stakeholders. I want to talk to you about the details, the technical details about the vulnerability, the actual attack that happened, and how could one prevent similar threats. Everything I'm about to tell you, it's been beautifully explained by some investigators, Heidi Weiler, Peter Krakenhesky, Anto, all these guys, all these folks at Coinbase have done an amazing job at explaining the whole investigation in multiple parts. So lots of the things that I'm about to tell you are things that I actually personally learned from their investigations. I will be actually using some cool diagrams that they have, some cool graphs, some calculations that they use. So lots of things are based on this article and many others I was able to find, but I would say that this has been the main source for my investigation and for this talk. I will also be showing you code which is available in GitHub, in the GitHub of Euler. I will be showing you a proof of concept and I will be showing you transactions. So lots of things to cover. Again, I will stay away from all the drama, all the news, the headlines and whatever. I just want to stick to specifically to the technical parts of it so that we can learn the real thing from it and we can do better in the future altogether. Before we jump into the very details of the vulnerability, I do want to do a brief introduction about not only lending protocols but some mechanics about Euler that are fundamental to understand the actual vulnerability and the attack. I cannot explain the real thing without giving a brief introduction to it. So I will just glide through it. Lending pools, right? So you deposit assets, those assets become collateral. The lending pool is able to print some tokens, in this case would be the E tokens for Euler. You could also call them interest-bearing tokens, LP tokens, yield tokens, whatever you want, so, right? So you deposit something, that something becomes a collateral in the system, and the system gives you back E tokens that represent your position in the system so far. If you want to redeem those E tokens, you can do so, and you will get your collateral back, right? So you burn the E tokens, you get the underlying asset back. Simple as that. That not only works for a single asset such as DAI, but for multiple assets, right? So these lending protocols have grown in complexity and are able to handle multiple assets. This is very much similar to how Compound, Aave, and many other works, right? So nothing new in that regard. Why would you want to deposit something? Well, because you can actually borrow something else in exchange. So a user might deposit DAI, will get some eDAIs in exchange. Those DAI will go to the DAI reserves, in this case Euler, and some other users might not be doing such thing with DAI, but might be working with wrapped ether. So in that case, as a user that you have deposited DAI and you have now DAI collateral, you might be able, depending on how much DAI you deposited, you might be able to get some wrapped ether as a borrow. When you borrow something, in this case in Euler, you would get D tokens back and the tokens back. Not only that, but also you will get, of course, the wrapped ether that you're trying to borrow, right? It wouldn't make sense otherwise. Remember that these are over-collateralized lending protocols, so that means that you can only borrow a certain percentage of the deposited collateral value that you have. So if you deposited DAI, let's say 100 USD worth of DAI, then you might get 75 USD worth of wrapped ether, for example. There is a very important attribute of positions, in this case in Euler, but this is true for many other lending protocols as well, which is called the health factor. The health factor is essentially the professionals of DeFi might not agree with this description, but let's go to the very fundamentals. It's just how much you have deposited over how much you have borrowed, right? So ideally, a lending protocol wants all of their users to have a health factor above 1. Otherwise, that might be problems, right? Otherwise, some positions might go under collateralized. That might be the case when there are price movements in the market, and the health factors might go below 1. If they go very much below 1, That means that all the money that they have borrowed is valued much more than what they have deposited, and they might not have the incentives to repay their debts. Okay, so a lending protocol wants to have always the all positions above 1 when it comes to their health factor. When that's not the case, then liquidations happen. I won't explain liquidations. Probably there are far smarter people out there that can explain liquidations in YouTube and articles and everything. Let's just say that liquidations are a mechanism that DeFi protocols, in this case, implement, but liquidations are a thing in traditional finance as well, of course, where somebody repays the borrower's debt and in exchange will seize part of the borrower's collateral. Why would they do that? Well, because they will have a discount. They will have a way to make a profit out of liquidations. Otherwise, probably nobody would do them. So, for profitable liquidations, these lending protocols offer the collateral at a discount. And not only that, but also when the health factor is lower, then the discount over the collateral will be higher. I think that's a particular case for Euler. I'm not today that much familiar with how compound and other works in this regard, but for the sake of this explanation, that's how Euler works. The lower the health factor, the higher the discount, right? Well, all of the things that I'm telling you are actually implemented in code, okay? You can go and take a look at them. You can go to Euler's code and take a look at them. Everything is in GitHub, so you will find a liquidate function in the code. And if we go to this compute liquidation of something, there's a function in here that will check exactly what I'm telling you. If the collateral value is greater than the amount of debt that the position has, then there is no violation of the health factor. So everything should work okay and no liquidation should happen. Otherwise, the function continues here, and if it goes to this point, it means that the collateral is worth less than the liabilities of the position, and that means that there is a chance that the position can be actually liquidated by the caller. Okay? So again, don't take my word for this health factor thing. You can go to the actual code and see it for yourself. That's a good exercise usually. There's another thing, very important in this case, very important, which is called invariants. Invariants are essentially properties of a system that should always hold. If an invariant at some point changes, meaning it's a variant, not an invariant, that means that something has gone completely wrong. Euler, surprisingly enough, which is something like super good, has many invariants listed publicly about their system. It has all this list of invariants. Again, you can go to the code and see it for yourself. There's a markdown file that you can go to. There's this particular invariant that says no protocol action should be able to result in an account with risk-adjusted liability greater than the risk-adjusted assets, meaning that check liquidity is failing. Okay, so it's essentially saying that no protocol action, that means, let's say, no function call, no action that happens embedded in the protocol, should be able to create a position or trigger a position that has a health factor lower than 1. Okay? So all protocol actions should make sure that there is enough liquidity in the position such that the health factor is always cool, it's always nice, it's always above 1. If there's a protocol action that happens that suddenly moves the health factor of a position to an amount lower than 1, then this invariant would have been broken. So there should be somewhere in code where this invariant is always checked. And it's probably this check liquidity function. If we go to the check liquidity function, yes, of course, there is a check liquidity function. This check liquidity function we will see in a moment that is called like probably everywhere in the code base. In many actions. There's an internal call that happens as well to a module which is called the risk manager. So we will go to the risk manager and we will find the internal require liquidity function. Okay? So if we go to this require liquidity function, there's a super important require statement that says that, well, always when you are requiring liquidity, it means that the collateral value should be greater or equal than the liabilities. right? Otherwise, there is a collateral violation. Essentially, again, coming back to the slides and coming back to our explanation, it means that the code is actually checking this. Okay, there is some part of the code that is checking that the health factor is always greater than 1 when there is a protocol action happening. I mean, it's trying to protect, all of these functions are trying to protect this invariant. As I told you, this check liquidity, and of course the internal required liquidity that gets called, it's probably everywhere. And yes, it is. So it is in the withdrawals, and as I'm showing you this case, it is when you do self-borrows, which I'm not going to explain today. It's when it happens in self-repays as well. It happens during actual borrows of assets in Euler. It happens even during transfers of tokens. I mean, it's in many fundamental actions of the protocol. It's always calling this check liquidity function, because again, it's trying to always protect the invariant. That's how you protect the invariant. Otherwise, it might become a variant. So in any protocol action that deals with these D tokens and E tokens, you always want to be checking liquidity. Yes, they are everywhere. Are they everywhere? Were they everywhere? Probably you see where this is going, right? So no, they are not everywhere, because at some point the Euler developers included a change in their code base and included this fatal function that is called donate to reserves. Essentially, this function was included to donate E tokens to reserves. At some point, they realized that there might be some dust in some positions, and perhaps that dust would complicate some calculations or might be unnecessary for some scenarios. So essentially, what you could do, you could call donate to the reserves and move those E tokens to the reserve of the protocol. There's something missing. Is any in this function? If we take a look at it, again, we can go to the actual code. You don't need to trust me. You can go to donate to reserve, and it's right here. Okay, so it's in the code. If you scan it, you will see that if you are paying attention, there is something missing, and of course there's something missing, otherwise I wouldn't do in stock, which is essentially the check liquidity. Because this function is lowering the token balance of a position, it's mingling that, it's changing that, it's affecting the health factor of a position. Because if it's changing the number of tokens in balance, it's essentially changing the health factor, it's decreasing the numerator of the ratio that I showed you before. Remember, the health factor is the amount of assets that you have deposited, which is represented by the number of tokens, over the amount of over the liabilities that a position has, which is represented by the number of D tokens. So if you are decreasing D tokens, it's essentially you are pushing down the health factor. Which, remember, as we saw in the invariant, that's a pretty sensitive action. So if you are not calling check liquidity, things will go wrong. This new feature broke one invariant. So what could an attacker do? And actually, what did an attacker do? Well, there are three essential steps that the attacker follows to exploit this lack of checks in the health factor of a position. Number one, create a huge position in Euler. That means deposit lots of things and borrow lots of things. That's essentially it. So number two is lowering the health factor, right? Executing this donate to reserves, this function that is not protected, this function that can help an attacker break an invariant, very important invariant of the system. That happens in step number two. And step number three is liquidate the position for profit. Remember, I told you that liquidations are profitable. And the lower the health factor, the more profit that is an attacker could make. So step number one, position super big. Step number two, call the vulnerable function. Step number three, liquidate the position and make a profit out of it. Those are the three essential steps. Let's see number one. Whoa, too much. Probably too much. Look, there's this transaction trace that I'm about to show you for USDC, for the USDC pool of Euler. Again, everything's here. The link will be in the description. Otherwise, you can find it in this beautiful article as well. And you can see all the nested calls and all the creates and all the transfer and the deposit and the static calls and the logs and everything. Everything is here. Everything is traceable. You can see it by yourself. What I have done, instead of showing you this, I have copy and pasted and cropped and highlighted some parts so it is easier to understand. Usually when you do this analysis over traces of transactions, it's not like super necessary to know every single step. You can actually understand the big picture by just looking at the most important steps. Okay, so that's what we are about to do. Again, if you want to dig far deeper into it, the transaction is there for you. You can scan it all by yourself. Not only this one, but even other ones. We are reproducing how an attacker created a huge position in Euler. So, huge position means lots of assets, and lots of assets probably means flash loans. So yes, the attacker took a flash loan of over 200 million USDC from Aave, and you can actually see that. It's highlighted in there. You can see how the flash loan function is being called, and the execute operation callback is being called on the attacker coordinator contract, one of the contracts that the attacker is using for this exploit. It's using actually 3 contracts, the coordinator contract, and then it creates 2 additional contracts, the borrower one and the liquidator one. Remember that the attacker needs at least 2 contracts. It's also using the coordinator, but needs at least to simulate 2 actors in the system. One, a borrower that is going to create a huge position. That position will become insolvent, and then it will come with the liquidator to liquidate it and make a profit out of it. So that's why it's creating 2 contracts. We are going to see later the contracts. So the next step is transferring all USDC. You can see this transfer call on the USDC contract to the borrower. Okay, so it's moving all of these flash loan assets to the borrower. It calls the borrower, passing execution control to the borrower. Once that's done, what we are seeing now is, remember, this diagram comes from the blog post I showed you before, but what we're seeing here is that all USDC of this flash loan is in control of the attacker right now, okay? And the attacker is targeting a pool that has almost 34 million USDC, right? So that's what the attacker is targeting. And for that, it has acquired 210 million USDC. Let's see how the attacker proceeds with that. Now the attacker creates a huge leverage position. I'm not going into the details of that. Again, DeFi experts are far smarter than me and can actually explain you what a leverage position is and what it's actually meaningful for. But just let's say that it's about like depositing stuff, borrowing, and what you borrow you deposit it again and you borrow it again, and so on and so forth. So you make a huge cycle out of it. DeFi is complicated. And once that happens, the attacker is able to do this. It's able to increase their position in EUSDC, those E tokens that Euler means, to this huge number, and the debt to this huge number as well. But even though they are both huge, the thing to notice is that the yellow thingy is taller than the red thingy. So that means that the health factor of the position is still over 1. Okay, so the position is not yet insolvent, is not under collateralized. Everything that the attacker has done so far is by the book, is by the rules. Everything is okay in terms of how the protocol is behaving so far. So the attacker took a flash loan, deposited it, and created a leverage position, has lots of E tokens, has lots of D tokens, but everything is cool. And also notice that the pool size is over 200 million now because all the USDC has gone to the pool. Okay, so we had 34 at the beginning, you add the 210 now, and you have 244 now. Okay, so basically everything is cool so far, but the attacker moves to step 2, where it lowers the health factor of the position, executing the donate to reserves call, and it's essentially here. You can see that in the transaction trace. It's there. So what the attacker does is donating 700 million E tokens, calling this flawed function. It's moving these USDC tokens, these E tokens, which are the EUSDC tokens that Euler means, is moving them to a reserve. It's essentially moving them out of the position of the attack. So remember, if this is the call that is being executed right now, in this call we're executing this code in smart contract, so it means the health factor is gonna go down. And if the health factor is gonna go down, then the position is now ripe for liquidation, because the attacker, it hasn't changed their D token amount, but it has decreased the amount of E tokens in the position. Remember, the attacker starts here and now move here. See how the yellow thing moved down. So the health factor is lower than 1, can be liquidated. And let's go to step 3, which is liquidate the position for profit. That was what the attacker was doing. So, following with the transaction, after donating to reserves, we can see the actual code to liquidate. We can see the actual code that calls the function liquidate, right? So it's calling this exact function right here. That's what being called in here. So it's liquidating the position, and if we go in the nested calls within liquidate, again, lots of information, lots of data, and don't worry too much about it. Let's see the last thing that happens at the very much at the bottom. So during the liquidation, the attacker is able to move these E tokens, this EUSDC, from the borrower to the liquidator. See that transfer that happens of USDC. Sorry, of EUSDC. It's essentially. Once that happens, once the attacker gets these E tokens, now the attacker can actually redeem them. So we see again a call to withdraw. It goes with these E tokens to the lending protocol and withdraws the underlying collateral. The underlying collateral is this pool size, is this 244 million that is available in the pool at this time. So, at last, remember that even if the attacker was able to take the whole USDC that was stored at Euler, the attacker has still to pay their debts. The attacker took a flash loan from Aave. So, the attacker returns the flash loan and pays some fees for it. And that's essentially it. The attacker has just made a profit of over 34 million USDC, stealing all of these assets from Euler. That was the amount in the initial reserve that we saw at the beginning. Huge, okay? Huge attack. Do you want to see a proof of concept? Probably yes, otherwise you wouldn't have watched so far. So let's go to it. There's a fantastic investigator, again, Peter from Coinbase. He's awesome. He coded a very detailed, very comprehensive, super understandable proof of concept that is available in his GitHub. That's the one that you should probably go to if you want to see the whole thing happen. Okay? So the exploit even closely replicates the reverse engineer contract that he analyzed. Okay? So it's very detailed. It goes through multiple pools of USDC, WBTC, WEther, staked Ether, and so on and so forth. Even DAI. I mean, it goes on and on and on. Okay? So the whole exploit has been reproduced in this proof of concept. What I have done is I have simplified that so it's easier to understand for us human beings. Okay? So I have that in my editor here. This is a Foundry test, and as in every Foundry test, we start with this very simple template. There is a fork of mainnet being created to the block before the attack happens. Then this example deploys a coordinator contract and call this initiate attack function on the coordinator contract. Again, remember, simplified version of everything that Peter has done wonderfully in his proof of concept. So if we go to the coordinator contract, we go to the initiate attack function. There are some hard-coded values and parameters that these investigators found in the reverse engineer contract, and these are the ones that I have taken for my concept. Okay, so essentially we are going to be working with USDC. This is the address of the tokens, the address of the D tokens, who's going to be the provider of the flash, or in this case ABV2, and some initial calculations of parameters and configurations for this attack to make sense. I should also mention this code is based on the Foundry template by Immunify that is done to create proof of concept exploits. Okay, so if you want to see more details about it, you can go here to the Immunify team, GitHub, and see their template, which is awesome, and we are going to be doing a video soon about how this template works. Okay, so let's go back to our code. We looked some things about the beginning of the exploit, the balances, we log some actions, and then the code takes a flash loan and everything happens within the flash loan. So before we proceed, let's run this so we make sure that we understand how things are logged, and then I'm gonna go into the details of it. See, this is the result. We have just for mainnet, and this proof of concept attack has been executed. So at the beginning, the Euler balance was over $34 million. Then the attacker balance was 0 at the beginning. The attacker borrowed this amount of assets from Aave. Then the attacker deployed contracts, created this leverage position, and has called already donated to reserve at this point. See that the debt is greater than the deposited assets. Then comes the liquidator. The liquidator attacks this position, targets this position, and see that it has taken all the collateral. The bad borrower still has debt on it, and the liquidator has made a profit of over $34 million. Finally, the attacker withdraws those C tokens and gets the USD and pays back the flash loan. And at last, you will see that the balance of Euler is 0 USDC. Remember, at the beginning was over 34 million, and the attacker balance at the end is this over 34 million. Essentially, the attacker has stolen money from Euler successfully. So let's go to text flash loan just briefly, because it's a function that comes from the template, so we won't spend too much time on it, but it's essentially going to the flash loan providers, in this case Aave, and it's gonna ask for the flash loan, for this flash amount. Then within the flash loan callback, the attack will be executed. That's the function here. So the attacker, as we saw during the transaction, will actually create the bad borrower contract, which is somewhat similar to this one, probably far more complex, but you get the point. Then there is a liquidator contract being created, again following to what the transaction was doing. Let's see that here. We can see that within execute here, so it's highlighted already. So the create call is done here, and the internal create call is done here. Okay, so the borrower contract is being created and the liquidator contract is being created, very much similar to what we are doing in our proof of concept. So the coordinator deploys the bad borrower deploys the liquidator, which is this one. It's gonna be used later. Finally, the coordinator now transfers the amount being flash loaned to the bad borrower and passes execution to the bad borrower to the generate bad loan function. So it goes here. Now the attacker using this contract will create the leverage position in this internal function calls to the Euler protocol, and will call the flawed function donate to reserves. This is where the actual vulnerability is exploited. Once that happens, the bad loan is already generated, so that means that the attacker can pass execution to the liquidator contract, in this case calling its liquidate function, and see that the attacker recovers some information from Euler so that it has some necessary data to trigger the liquidation. It calls the liquidate function in this case and essentially liquidates the bad position that was generated by the bad borrower. It logs some stuff and checks that it has received these E tokens back and withdraws them all. Okay, so at this point, the USDC balance of this contract should have been increased, so that later in this function call, these USDC are moved to the coordinator contract and last. Okay, so we see how the coordinator is able to manage the whole thing, taking the flash loan, transferring the assets to the bad borrower. The bad borrower is in charge of generating the bad loan. It does it here. Then it calls the vulnerable function, passes execution to the liquidator contract. The liquidator contract gets some data, liquidates, withdraws, and moves funds back to the coordinator, so that at the end the liquidator will be able to pay back the flash loan and everything. So that code is here. That's running again. So you see that again, this is immediate, and this is actually run against mainnet state. Okay, and a fork, of course, in a local environment in my computer. And this is the whole attack for the USDC pool, right? Very interesting thing. If you want to learn more, there are many other resources. Again, I'm not reinventing anything here. Everything I learned from these awesome researchers in the community that are sharing cool stuff out this exploit. Again, this Coinbase article is marvelous. Check it out. Go see the full proof of concept exploit coded by Peter. There's a link here to mine, which is again a very much simplified version that I just showed you. Rekt.news usually covers many security incidents in the community, and Omniscia as well did an interesting postmortem that you can check out. Okay, and probably many other resources as well in the community, and Twitter threads and YouTube videos and everything to learn from it. Okay, thank you very much for watching. That's been us, the Red Guild, covering what happened from a technical standpoint during the Euler incident. See you in the next one.